Now, I normally let students choose at this point in time which of these reactions on slide 22 they would like me to work out the mechanism for. They all pass through a common mechanism, and you are accountable for all of them. You need to be able to show the reaction of an acyl chloride with a carboxylic acid to make an acid anhydride. You need to know how to take an acyl chloride and an alcohol to an ester, and an acyl chloride and an amine to an amide, and also an acyl chloride with water to the carboxylic acid. The book shows the mechanism for the acyl chloride and water reacting to make the carboxylic acid. So I'm actually going to show one of the others, and since you're not here to ask, I'm going to take the acyl chloride and the carboxylic acid to make the acid anhydride. Now, some of these reactions are done in neutral solution, some of them are done in acid solution, and some of them are done in basic solution. You really need to pay attention to what's on the arrow in order for you to know what it is you should be doing. So with these carboxylic acids that we are using, we're going to use a weak base like pyridine, because we don't want to necessarily deprotonate it right off the bat. We will want to deprotonate it, but not initially. Okay, so again, we always think about acid-base chemistry first. And if you do this acid-base chemistry between the proton on the carboxylic acid and the aromatic amine, you would be producing a corresponding conjugate acid-base pair that really is no weaker or stronger. And so it's not very favorable to do that at this point in time. As a result of that, you need to be thinking about nucleophile electrophile chemistry and identify the best potential nucleophile. Now, you've got an oxygen on the acyl chloride and a chloride, and a couple of oxygens on the carboxylic acid. Now, the oxygens that form the double bonds are typically not the best nucleophiles, but they could be in some circumstances. It would be better to choose an oxygen that only has single bonds to it. So it's actually the oxygen of the carboxylic acid here that adds to the acyl chloride here. And the acyl chloride is very positive in terms of its oxidation state. Now, when this adds, you do break the pi bond between the carbon and the oxygen. Once this has occurred, we need to be able to draw the new tetrahedral intermediate. And you're going to note that because I added two neutral molecules together, you're going to end up with a neutral tetrahedral intermediate. That's as it should be. Now at this point we've generated a better acid in the solution, so the pyridine's job is to kind of be here to do that proton transfer to the solvent. That's its entire purpose. So the nitrogen here will use its lone pairs to pick up this proton and will give the electrons back to the oxygen. And we're doing this so that we no longer have a good leaving group with this oxygen. We don't want to be able to kick out this neutral molecule. So that's why we're going through this process. Alright, so now we're going to redraw the molecule minus that proton. It's no longer there. We're still going to have this tetrahedral intermediate. Okay, and off to the side, which is just a spectator now, is this protonated pyridine. It doesn't do anything really for the reaction at this point. What we are going to be doing is, of course, reforming the pi bond to the carbonyl carbon and kicking out the best leaving group. The best leaving group is the chloride because it is the corresponding conjugate base of a very strong acid. So it's the best leaving group at this moment in time. So we reform the pi bond and we kick out the chloride. Now once that's done, we have the acid anhydride. And that was the goal. Acid anhydrides are more stable than the acyl chlorides, so we can make them from acyl chlorides. And then you've got, of course, your spectators down here. Now you could do very similar chemistry using an alcohol to make the ester. You just need to use the oxygen of the alcohol as the nucleophile toward the carbonyl carbon of the acyl chloride in the first step. Or you could do this with an amine. And now, as you hopefully remember, amines are very good nucleophiles as well. And you could use the nitrogen's lone pair as the nucleophile toward the carbonyl carbon. And all of these would do very much the same chemistry. With the amine, you do need to include a base so that you can deprotonate that nitrogen after it has added to make the tetrahedral intermediate. Otherwise, you've got a good leaving group. In the case of the ester, an alcohol by itself could come in and do the proton transfer to the solvent. It's favorable acid-base chemistry since it doesn't make a stronger acid-base pair. They're of equivalent strength. And you may want to try running through those on your own. You never know what kind of a mechanism you might find on a quiz. So, I kind of recommend you take some time doing that on your own.